Okay, so good morning to all of you. Thank you for coming today. It's my pleasure to introduce Juan Uriaguereca. Juan was born in A Coruña, in Galicia, a bit farther to the west, right? He was a student in this house, actually. He got a diploma here in philology, right? Yeah. And then he moved to the US, where he got a PhD degree in Connecticut. Since then, he has been developing a very, say, fruitful and brilliant career there in the US. He's a professor in the University of Maryland, but he has always kept a link, a very close link with, say, the science, both in Basque Country and more generally speaking with Spain and many of our institutions. He's an expert in biolinguistics, according to his webpage. Well, you will see and you will judge what that means. I remember the first time I saw his name was back in 2007, where there is a journal here published in the Basque Science System. It's called Thick Network. Thick is the name of this. I think it's Centros. ¿Cómo es? Centro de Investigación Cooperativa. Well, this is a network of centers who are editing this journal that is very nicely done. You can have a look on the web. And there was an article by Juan whose title was, I noted the title in English, but now I forgot. It's Jilguero más chimpancé igual a humano. How do you translate this to English? Jilguero is
something like finch plus chimp, which is finch, chimp equal human. It was a bit of a joke.
Bird plus a chimpanzee, so a monkey is equal to the human. It's very interesting, actually. It's online. And then, Juan comes regularly here to visit family and also meet some colleagues. I told him, listen, come to Deusto and deliver this talk, and here he is. So it's in principle, it's something that should be accessible to us, right? So it's matrix analysis, so we should be able to follow. Okay, thank you, Juan.
Thanks very much. Thank you. So it's a pleasure to be here. I actually come from a background that is more formal than what I learned later in life, because I was interested in economics and so on. And so when linguists talked about matrices, I said, well, what do you mean by that? Do you mean it seriously? And I always thought that you should mean it seriously. So anyway, part of what I want to do today is show you a way in which you can take matrices the way linguists or computer scientists use them as lists of features. When you give them a mathematical interpretation, I think interesting things happen. That's the gist of the talk, and I left a paper with Enrique where my colleague Roman Oruz and I, he's on his way here. He's at the physics center in Donosti, where we wrote the math behind what we're doing, so you can examine it in more detail. But let me give you the gist of why we're even interested in that. So what do we care about? That's the young Chomsky, by the way, the very young Chomsky, Noam Chomsky. His big contribution to the field of linguistics was to ask about possible and impossible syntactic patterns. Do you mind if I take off my jacket?
No.
With the microphone. Oh, yes. Okay. All right. Well, good point. I never thought about that. Okay. I'll just put it here. There you go. Okay. Good. Thank you. That wasn't planned. First of all, and I think as mathematicians, you probably don't need to be persuaded too much about this. You want to put aside meaning prejudices. So just as you shouldn't say that the square root of minus 1 doesn't exist because it has no meaning, although that was said at some point, and you actually can find some meaning to it and very useful meaning to it, linguists shouldn't be tempted to say, well, meaning is all there is to language. I mean, think of a famous sentence by Chomsky, which now is so famous that it probably has gotten some metaphorical meaning. But imagine the first time you hear the sentence, colorless green ideas sleep furiously. Well, if you go through that composition, it has no meaning. But his point back in 57, syntactic structures, was that, yes, it has no meaning. And statistically, you're not going to find it in any, well, nowadays, yes, because everybody talks about that sentence. But if you come up with a similar sentence to that, you're not going to find it statistically. But it has a different intuitive feel than something like furiously sleep ideas green colorless. I mean, if you just listen to that yourself, you see that when we put a star here, we mean that they're unacceptable in a different way, in a sort of formal way. It's kind of like if you say 2 plus 2 equals 0, and you say, okay, well, that's wrong, but it has some, the syntax is fine, versus 2 plus equals 4. Well, that's just the syntax is wrong, right? Similar situation here. So we want to figure out regularities of that sort as linguists that natural language presents. And if you think of it for a moment, it's actually quite interesting that universally, as you look at languages, they present regularities. I'm just going to give you a few here so that you get a feel for it. So you have nouns, verbs, adjectives, adpositions. They could be prepositions or postpositions, like in Basque or in other languages. But those are universals. So an obvious question that you want to pose as a mathematician or as a formal scientist is, well, why those and not others? Why? You could imagine other categories, dynamical versus static or male versus female. I mean, you can categorize the world in infinitely many different ways. So why those 4? Why 4 and not 2? If you just needed a combinatorial system, 2 would be plenty, right? In fact, that would be most elegant. So why 4? Or if you're going to go for more than 2, why not 10, like many numbering systems, or 6, or your favorite, right? N, right? You could even imagine, why don't we have as many as senses or something? But nothing of that sort happens. It's those 4, and that appears case after case. It's also the case, universally, that somehow nouns and verbs are more essential, more architectural, more basic than adjectives and prepositions, right? I mean, so if you want to edit your paper, there's many places where you can take away your adjectives and so on. But if you take away your nouns and verbs, the whole thing collapses. So in what sense are they more basic? Those are questions that we need to think about. And the phenomenon that we call syntax and the study that syntacticians pursue is the idea of putting together these kinds of patterns in quasi-algebraic ways. In fact, I'm hoping that those quasi-algebraic ways are literally algebraic ways. So we want to use formal tools to tell us why the ones that appear are the ones that appear and what are possible combinations and so on. Syntacticians these days use the term merge to refer to things that get together. Over the years, I've been around for a long time. They've been calling these things many different ways, but it doesn't matter how we call them. Let's just call it merge. The idea is you put 2 words together, 2 phrases together, and you get a new one. So it's a recursive procedure of combination. Now, it's interesting that some of you may have seen little objects like this, sometimes called trees or phrase markers. They make a substantive claim. So, for instance, if you decide that this is the constituent structure, you're basically deciding that there is a verb phrase, that there is such a thing as killed Caesar, that in some sense is a unit, and leaves Brutus aside. Now, of course, just to give you a sense, you could have done many other things, right? You could have done it flat, or you could have done it like this. So why is it? What's the reason behind that? I'm not going to spend too much time today unless somebody presses me in questions and so on, but there are empirical arguments for this. It could have been any of the others, maybe in another possible language, actually not a human language, because in human languages we apparently we don't have this, which is logically possible, obviously, but it doesn't appear to be encountered in human languages. I don't know if there's ever extraterrestrial intelligence, whether we would find something like this. But
why do you say we don't have this?
Yeah, empirically, we haven't found any language where you find arguments that this constitutes a unit, that the subject and the verb constitute a unit, and the object is outside. I mean, it's a logical possibility, but once you examine the details, it doesn't appear to be the case that exists in human languages. So that's a puzzle, right? Why do things work that way? And by the way, the empirical arguments are of the following sort. So for instance, I mean, there's a bunch of them, but I'll just give you one. You can put adverbs like never in between the subject and the predicate. So Brutus never killed Caesar, that's fine. But if you try to put it here, in a language like English, this may vary in other languages, you start getting a difficulty. Right, so Brutus killed never Caesar degrades in acceptability for speakers. Okay, actually, for this particular adverb, you get something similar in Spanish, right? Brutus nunca mató a César, fine. Brutus mató nunca a César, problem. Okay, all right, so there are arguments of that sort that suggest that there is a verb phrase, and that's part of what our systems need to capture. There are others, and I won't spend too much time on this, that basically suggest that yes, this is a unit. Now. In addition, we have terms that we take from traditional grammar, like head complement, that we want to capture by way of this merge operation. And it's interesting to say that even in such basic head complement relations and just head complements with no subjects, you start getting recursion. So for instance, consider something like kill relatives of friends of senators with lovers of poems about New York City, and you can go on and on and on. And you're only getting head complement. By that I mean something like a verb and its complement, a noun and its complement, a preposition and its complement, and so on. And it's already recursive, because here I can put whatever you want here, goes on forever. And I haven't introduced any subject or anything like that. So already in this very simple relation, you already have recursion. It's also interesting how picky these relations are. Every time you get a star, I mean unacceptability. So for instance, nouns typically can optionally get a prepositional phrase as a complement. So portrait of Rome, that's fine. But if you start putting any other combinations, like a verb or an adjective, you start getting junk. Even when the corresponding verb would make perfect sense, right? Portray Rome is fine, but portrait Rome is not. You need to say portrait of Rome, okay? They are all very picky. You sort of get the reverse situation. So destroy Rome, but not destroy in Rome, even when it would have made sense, okay? So they are extremely picky. Similarly with adjectives, proud Rome, bad, proud eat. You could be proud semantically of eating, let's say, but that's not the way you say it. You have to put a prepositional phrase. And similarly with preposition, you take a noun phrase. So there are regularities of that sort which are either 100% or statistically overwhelming. In some instances, you get more than 50% of categories of that sort, or in some cases 100%. So again, we need to explain that. I mean, why is it? I mean, it's not like you roll your dice and you get some of these combinations, or in Basque it's this way and in the next language is the other way. In Basque it's going to be the same way. The postposition is going to be at the end, but you're going to get the same restriction. So that's peculiar. That's something we need to explain. So idealizing a little bit, just because we're scientists, we want to get to the core, you basically have something, linguists use the word projection because they want to generalize over all these cases. So a noun projects a noun phrase, a verb projects a verb phrase, preposition projects prepositional phrase, and so on. Error. Sorry, that should be an A. Yes, so if you see this should be adjective projects an adjectival phrase. This is a preposition, projects a prepositional phrase. So my apologies, this is a labeling mistake. But the important point is here, right? You get a head which projects with a complement, and the selection is picky. Not any of all four projections count. Some do, some don't, and we need to figure out how that works. So just as universally only those four categories exist, there are regularities like this. Only P-headed complements go with noun or adjective, or generally N-headed complements go with VP heads. This is just the generalization. There are regularities like that you hope to capture. In addition, there are other regularities, just to get you a feel of the things we need to explain as syntacticians, where you probably have thought about interesting, like think of passive voice, right? An emperor was killed. The meaning of an emperor was killed is no different from the more convoluted expression, there was killed an emperor. It conveys the same meaning, okay? But obviously in one case, the logical object, the guy that gets killed, is in complement position, whereas in the passive, it's clearly in subject position. You get the same thing in Spanish, right? Un emperador fue asesinado un emperador. Both are fine, okay? So there is in some sense, this is one of Chomsky's biggest insights, there is in some sense a displacement, right? There is a displacement that is possible with objects like an emperor, which can appear grammatically as subjects. By any means, when you have a passive like an emperor was killed, it's pretty clear that this is the subject grammatically. For example, it agrees with the verb. You say an emperor was killed, plural, emperors were killed. So clearly this is behaving like a subject. At the same time, though, it's clearly the logical object, right? When you say an emperor was killed, he didn't do the killing. In fact, you can say an emperor was killed by an army, and that's the agent, okay? All right? Now, here's the punchline of this little thing. These displacements only happen with noun phrases. Systematically, only happen with noun phrases. Why? I mean, why not adjectival phrases? Why not prepositional phrases? Why not verb phrases? Why are these restricted to the noun phrases? That's part of what we need to explain, okay? I mean, I'm cutting corners a little bit because I want to just give you a panorama in 15 minutes, but that's the essence here, that there are possible and impossible patterns, and we want to figure out what is the algebra behind. Is there a rhyme and reason to this? One last pattern that I think is worth reflecting on. What's in a name? Well, think about the things you can name. I mean, logically speaking, we're scientists. We can name whatever we want. We could name, certainly you can name the emperor of Rome. Here it is, Caesar. And you can even use a pronoun, him, okay? But now, as scientists, let's take a famous event, Kill Bill, okay? Can I name that? Sure, I can arbitrarily name it, but it's not what you find in languages. Languages don't name events denoted by verb phrases, or they don't use pronouns for it. Similarly with a bunch of other, proud of Rome. Caesar was proud of Rome. Can you name that? Name just being proud of Rome. Again, arbitrarily you could, but that's not what you find in languages. So names seem to be restricted to noun phrases in this systematic sense, and that's surprising. Okay? There's another interesting property of noun phrases. Remember, they displace and they can be named. Right? Those are interesting properties that our systems need to figure out. Why? Well, first of all, because we are curious as scientists, but also because these little guys, we have a lot of research showing that by the age of 3 or so, hi, this is my co-author, Roman, coming from Donosti. So I'm just starting, and I haven't gone to the formal stuff yet. So these little guys, we now know by now that, by age 1-ish, they're already figuring out pointing and naming quite well. By age 2, my God, that thing begins to explode. The minute they go to kindergarten, by age 3 or so, that whole thing is in place. So whatever is going on is these generalizations that we're trying to figure out. Part of it must already somehow be in place in some sense. God only knows exactly how. That's part of what the biolinguistics project wants to figure out. What are the priors in that learning process? And part of it is acquired through data. Obviously, there's a dialogue between the two. But whatever is going on has to go on super fast. Okay, super fast and with very few errors. It's actually very interesting to see the errors they make. We can talk more about that later if you're interested in. So anyhow, here's the first proposal. This is a proposal that Roman and I have in the paper that we left that comes from the work. We call this the Jarrett graph because a physicist, Michael Jarrett, suggested it to us as a way to think of the issue the way you guys would in mathematics. So first of all, let's introduce some operators. I'm putting a hat. Whenever I get a V hat and so on, I just mean there is an operation which I'm going to try to be precise about. And descriptively speaking, all the facts about selection that we saw in the last slide, and if you want to, you can go back to that or see in the paper, could be generalized this way. So if you are a noun phrase, you can be taken by a preposition or postposition in a language like Basque. So this is your argument, and this is the result of that operation. Okay? Now, once you think of it this way, you get an interesting... This begins to be more the kind of thing that scientists do. Like say, okay, well, so there's a directed graph with interesting properties and so on. Of course, why? Why this, right? But at least it begins to be in a realm of things like, oh, well, all right, so these things are connected somehow. Okay? So that's step one. Introducing dependencies. Before I go on, because I'm going to, shift gears here and give you more precise meanings to this, for you, I suppose, these types of graphs are second nature, so nothing to write home about. I don't want to spend too much time, but if this is puzzling, let me know, right? All this means is that this is an operator taking this as an argument and spitting this as its value, okay? All right. Now, here's where we get into matrices, and where... this is where Roman and I started working together. And first week of class in Connecticut, they showed me this. This is Chomsky 74. And I was fascinated by this claim. Okay? This is a claim that Noam Chomsky made to say, look, these things you think about as primitives that come from the tradition, noun and verb and so on, they're not primitive. They are combinations of more basic dimensions of some sort. Okay? So you want to think of N and V not as noun and verb, but at a nominal dimension or a verbal dimension, which we're going to have to characterize. Okay? And his big intuition was that just as in phonology there are consonants and vowels, and consonants have certain properties that distinguish them from vowels, maximally so, right? A consonant is as different from a vowel as can be within phonology. Just as you do that in phonology, you could do that with the categories from the lexicon, from syntax. And that these features then are geared towards further properties that these guys have. So for example, if you are minus n, now notice, to say that you're minus n means to make a generalization about this guy, which is minus n, and this guy, which is also minus n. So the minus n guys engage in a process of what is called case assignment. So you do something funny to your neighbor, which you don't if you don't have that feature. So this is more abstract. It's a claim that is more interesting, that allows us to ask further questions. Moreover, if you look at the details of the paper where Chomsky introduced this, he makes this, it's an idea that has been around for literally centuries, but the idea that these dimensions are conceptually orthogonal. Just as consonants are vowels, and vowels are as different as can be, nouns and verbs, the noun dimension and the verb dimension are as different as can be. Now, when they use words like orthogonal and so on, for me it's like, whoa, what do you mean by that? I mean, do you mean orthogonal in the sense that they're perpendicular or something like that? In what sense are they orthogonal? In what sense are they as different as can be? I mean, that's not a trivial question, right? He doesn't resolve that. He leaves it there, and it stood there for years. I'm going to make a bold move here. This is one of the claims. As far as I know, we are the first one to make the claim in the paper that we're leaving. Here's the fundamental assumption I'm going to start with. By the way, I start with making the assumption that the dimension of n is 1 and the dimension of v is I, simply because those are things we know how to operate with. I mean, in a sense, any orthogonal formal entities would do for the purposes of what I'm doing. But I know how to operate with this because my math is very limited. I'm told that, yes, you can operate with others if you define the algebra, but I say, well, why not work with the guys we know? But I don't want to make deeper claims than these guys are orthogonal, and of course, those units are going to be orthogonal in some sense in the complex plane, okay? All right, so that's the fundamental assumption that the rest of the talk is going to be based on. By the way, jump in at any point if you want with qualifications and so on. Don't be shy. As a matter of fact, come closer. I'm fine here. You're fine there. Those physicists always hide in the back. Right? Now, and this is where when I met Roman, he started pushing me more in this direction. He said, well, look, if you were trying to do this seriously, in other words, if your job is to look at Chomsky's guys, this is from the linguistic tradition, and if you want to implement this assumption, Roman was saying, well, we should really go all the way. In other words, as mathematicians, you probably want to start using nice operators like square matrices, 2 by 2, simplest matrices, and put the n and the v in the form of 1 and minus I, in this particular case, put them in the diagonal of the matrix, and then see what happens if you operate with that. Okay? So this is the first one I blame you for. All right? Now, of course, once you move into this realm, either you're in La La Land, which is possible, right? Maybe it's all cuckoo. But it's interesting, right? Because now you can start asking further questions, right? You can start asking, well, so do these matrices add? Do they multiply? Can you run a tensor product? I mean, all the questions that you guys do for a living. Moreover, you can ask, well, what is the determinant of that matrix? And does it have any meaning? What are the traces? Do they have any meaning? And so on. And very soon, you start creating a vector space. If you operate with those matrices, you treat them as vectors, you can create a vector space, and you will see that interesting things happen once you get into that vector space. Okay, so that's where I'm taking you. So the first task is to translate the substantive graph that I showed you 10 minutes ago into a version that is now mathematically meaningful, where you can operate with. I have until 12 what?
Well, no, in principle you have until 11, so 1.
Until 1. Well, but I want to, at this point as we start getting into the math, don't hesitate to just jump in, because in essence you have the paper, you can see what we're saying, and if things are confusing, it's better to just slow down.
So this matrix calculus was also introduced by Chomsky?
No, this is us. This is us. Chomsky, well,
Chomsky matrices.
Well, we call them Chomsky matrices because we think the insight is here. Right. This was the big, bold move, and the idea that they're orthogonal. We call them Chomsky matrices to distinguish them from Pauli matrices, because as you multiply the Chomsky matrices, which are the ones where you have a 1 and an I, well, you can see it here. For instance, as you multiply this times this, you get, this is Pauli's Z and the negative version, right? So we distinguish Pauli matrices from Chomsky matrices. And they actually, as we will see in a minute, they form a group, which is interesting. That the gist of what we want to say is, look, all these properties you find is because this is a group. And then interesting things happen within that group. That's where we're going, okay? Anyway, if I haven't made any mistake, because unlike Roman, I don't use latex and so on. If I haven't made a mistake, that all the multiplications there are correct. Now, of course, there's a substantive claim here, right? We're saying that this operator is matrix multiplication. Right? That's substantive, okay? And if you do that, then you actually get two different results, which I'll get to, depending on whether you get this version of the matrix or that version of the matrix. The determinant is going to be the same, right? If you think of the determinant, it's going to be always the same, but the value is going to be reversed. Anyhow, this is in some sense progress over this, because then you can ask more questions, which here you really can't, right? Once you give me this, okay, that's cute, but once I give you this, you can push me into further questions, okay? Yes, so the only difference between this and this is that now I'm giving you the determinant. And now notice, if you actually compute, again, if I haven't made a mistake, if you compute the determinants, this is the determinant that corresponds to a prepositional phrase. This is the determinant that corresponds to a noun phrase, verb phrase, and adjectival phrase. Okay? As such, you could say, well, all right, it's fine, so who cares? Well, we'll see in a minute whether or not those moves get you new mileage or more mileage, or start predicting descriptions. Now, it is clear that one of these matrices is the identity matrix, right? Mm-hmm. And it is clear that the results of all these multiplications stay within this graph. So I think you can get that this is going to be a group. Okay? So then, as a group, then you want to say, all right, so what can we do with this group? What properties does this group have? And don't forget also that 4 of the categories in the group, these ones and these ones, are also part of Pauli's group, which has other matrices, namely X and Y, which suggests, oh, maybe there's more space here that we should explore as well, right? So all of that is interesting from the point of view of figuring out what the heck is going on. So here's, actually there's a mistake here. Let me see. Yeah, there's a mistake that I'll tell you about in a minute. Okay, so remember, part of what we want to figure out is why it is that many of the possible combinations do not arise. In other words, this seems to be what human language has used, which corresponds to the description. But surely, mathematically, there are many other combinations that are logically possible. So why is it that the language faculty, the human language faculty, hasn't used other properties?
Why are you describing everything through diagonal matrices?
It's an axiomatic decision. In other words, we are trying to see how far we can go with that, and we have gone as far as the paper we left. We could have done different...
Because diagonal matrices always commute, right?
Here's where I need you here.
Yeah, so the original motivation for diagonal matrices is that so that Juan was first operating with vectors, and then he was doing operations between the components of the vectors, right? And then when I left him, I told him, well, but if you just put this in terms of matrices, this is just matrix multiplication, let's say. Everything was kind of very natural, no? And then, but then we generalized this to the more generic case.
Yeah, so there are, once you go, these are all diagonal matrices, but as you start going towards the Pauli group, and I'll show you that towards the end of the...
So in control theory, there is this key concept of brackets, right? So the lack of commutativity is what allows you to generate unexpected, say, dynamics, right? So this is like when you park or unpark the car, you say left, front, right, back. So you are doing A, B, minus B, or minus A, wherever, and you don't get to the 0 because of the lack of commutativity. So these Lie brackets, or I mean, depending on who invent, I mean, in the nonlinear context, this is the Lie group brackets or the Kalman brackets in linear algebra. These are ways of exploring new dimensions in space.
This is very interesting. And what your point is that all of these are diagonal, all of these are commutative.
They are all commutative.
They are commutative. All right. So, well, let me jump in for a second. Let me.
Okay, but yes.
No. This is very important. Look, at this point, again, you have the paper, so you can read it. But I think the reason I'm finding your observation very interesting. This is the entire group that goes beyond the original 8 into 32, including non-diagonal ones. Now, as per your point, so the diagonal ones are going to be these ones, right?
Yeah.
These ones here, and these ones here, right?
Yeah.
Right. Now, if you actually look at the ones that correspond... So let me tell you what this is. In human language, aside from verbs, nouns, adjectives, and prepositions, you also have these little animals like the book, or like shall, I shall go. Right? We call them grammatical elements. They're absolutely central in putting together larger constructions, like a subject-predicate, because so far I haven't talked about that. And it has always been an interesting question, well, so what are those? What are those conjunctions, complementizers, all that fauna that is, in a sense, larger than the basic noun phrase, verb phrase, adjective phrase, prepositional phrase? Now, I find your observation is very interesting because in this categorization, which is a guess that we're making, the ones that are commutative are verb phrase, prepositional phrase, adjectival phrase, and noun phrase, the ones you were observing the comment for. The key ones where you start getting into this other, I would have to explain to you why we call them like this, but the intuition is that they start getting you into this other set of grammatical categories. They're not. And Roman, this is important. We might want to think about that because we hadn't made that specific connection, right? In other words, here's the substantive connection. And this is a guess that I'm coming up with in reaction to your thought. What if the lexical projections, verb phrase, noun phrase, etc., are the way they are because they are commutative? You want them to be commutative. Whereas these other guys, where you build the dynamics of the system, are the way they are because they are not commutative. I have no idea whether what I just said is true, but I think it's potentially interesting.
This is somehow a simpler way of seeing this is that you have dynamical systems that are diagonal, so meaning that each, say, component of the system is evolving independently of the other, and then you have this, the fact that there are these non-zero brackets allow you to establish links, right?
Right.
I mean, in the 50s, this was done by Kalman and Lyapunov, and these guys understood this, and then, this is a linear algebra exercise nowadays, but at that time was fundamental, is that you can control a system of a huge dimension just by a single control. But this control has to be somehow transversal to the system, right? And you check this by doing these Lie brackets. It's like a cubic Rube, or
Rubik cube. Yeah. Do you want to add anything to this?
No, not really. Concerning what you said, I mean, maybe it's the way it is because, well, actually, we had to generalize this to non-diagonal matrices and therefore non-commutative because we needed all this extra structure. I remember.
Right.
That was I remember we had some symmetry assumption at some point.
Right. There's an axiom of symmetry that gives us that. But anyway, let's think about this because frankly, at this point, we have no way of telling why it is that the lexical categories are all commutative and the other ones are not. Okay, so I think this is potentially an interesting way. Anyway, going back to where we were, what time is it, Enrique?
It's 12:38.
Okay, well, so again, let's go back to where we were. But this is very apropos because we could ask that question and we could attempt an answer because we have a formal system, right? Whether or not is the right answer, who knows, but that's... All right, so where I was in a similar... Yeah, so we introduced the group, and we started... I started asking the following. Here you have all the possibilities, all the combinations, beyond the ones that actually are attested. So if you look at all the combinations... So here's another way you could relate all four Chomsky categories. These are the Chomsky categories. But I'm combining them differently, okay? Or this way, or that way. Anyway, so you have 6 possible combinations, and by looking at it abstractly, you already begin to see, well, okay, yes, this is a possibility, sure, but if I do it this way, I cannot combine all 4. Now, if your task is to come up with a formal system that actually works as a recursive system in language, where what you're trying to do is connect a bunch of categories, number 5 and number 6 are pretty dumb choices in the sense that you're not going to be able to connect them all. Okay, so you could, from the point of view of coming up with what is called a semiotic system, a system that allows you to put together all these combinations and share it, this would be very bad choices for nature to take. But again, that's something that you see at this level of abstraction, not otherwise. Okay? Similarly, if you actually look at the substantive, so we made substantive commitments to these categories. For example, by Chomsky's assumption, this is his assumption in the 70s, the substance is that this particular combination is what he calls a noun. In fact, the way he came up with this is he guessed, of course he wasn't using a matrix or he wasn't using numbers, but he guessed that this was the right combination. Suppose he's right. Needless to say, that is not a formal assumption. That's a substantive assumption. You could have chosen any other decision. Now, if we make this decision, why am I highlighting the position of the n? Well, because remember, we saw empirically that nouns are very important to this system. we saw that noun phrases are the ones that displace. We saw that noun phrases are the ones that allow you to name things. I have no idea why humans take noun phrases so seriously. We could speculate, but let's just take it for granted that yes, for humans, nouns and the noun system is important. Okay? If you make that assumption and you assume that this is your noun, well, in this particular graph, number 3, your noun is not in the recursive core of that system. It's actually an output. Once you hit the noun, you're done. Right? So one difference between this and this, which is another logical possibility, is that here your noun is in the recursive part. If this is one of your nouns and you operate this way, taking this as an argument and spitting that as a value and so on, if you're doing it that way, the noun is in the recursive core. So the ones I put in red out of the 4 logical possibilities are the ones where the noun is an output. It just terminates the possible computation. Okay? That's another way to eliminate patterns, saying if you make the assumption, well, look, nouns are important. In that choice, you're putting them in the least important. You're not putting them in the driver's seat. You're putting them in the trunk or something. Okay? Again, that's a decision that we couldn't have reached without the algebra to be able to at least ask the question that way. Here's one more, and here's where there is a mistake. This is 1. I'm not going to spend too much time on this, but I want to correct the error in that this should be a 1 and not an I. Obviously, I'm just repeating this. Anyway, just to be quick about this and just tell you why am I doing, I'm eliminating, because I have to eliminate 5 of the 6 possibilities because only 1 exists in natural language. So the argument basically here is going to be that self-merge is possible in one of them but not in the other. You can look at the argument in the paper, but it is the same algebraic thing, right? Under certain conditions, certain things are possible, certain things are impossible, and only if you're making a formal system assumption does that make any sense. I want to start showing you the actual combinations that then become possible. So having eliminated 5 of the 6 possible combinations, you end up only allowing, within the algebra, within the group, you only end up allowing the ones that Enrique was talking about, the symmetrical combinations. So basically what you do is you take an adjective, you combine it with whatever you can combine it to be able to produce an element with determinant 1. And there's 2 ways you can do this. Obviously, it's going to work with this, but it's also going to work with the reverse. So in each of those conditions, you have what we call twin situations, right? Where you can actually get a projection by combining to 2 different matrices of opposite polarity. So those are the logical possibilities that we allow. One of them, I haven't explained this in detail, but one of them allows a situation of self-merge. So you also have the initial conditions of the system. The reason we worry about self-merge, by the way, is because think of the logic. Normally, you merge a category operator with a phrase. And that's fine. That's all I was showing you. But what about the first merge you ever produce when you don't have a phrase yet? So for instance, imagine you have something like kill Bill. Well, you pull kill out of the lexicon, you pull Bill out of the lexicon, put them together, but neither one of those is a phrase yet. It's not like kill the Emperor of Rome. The Emperor of Rome is a phrase. You have already operated with that, but Bill isn't. Okay, so you have to have a situation of an initial situation where you don't have a head and a phrase. And what we end up doing for those is self-merge. So for us, Bill, you will see in the paper, self-merges. So Bill merges with Bill, and that gives you a phrase. That's very technical, but so that when you, if or when you read the paper, so that you understand what problem that the self-merge is trying to solve. It's just trying to start the system. This is just a summary of what I just said. These are the actual combinations in the graph. If you actually look at the possible, so you basically see that the at positions combine at the core with the noun phrases. That's why you have a bunch of arrows there, and the system outputs either an adjective phrase and it halts, or a verb phrase and it halts. Okay, so this is now a mathematical rendition of the little the Jared graph we started with, right? Just in more detail. Now, of course, the important thing in all of this is that we haven't used any semantics, we haven't used any religion, we haven't used any sociological claims. No, these are just, to the extent that they are true, they're purely formal assumptions. And we think that's important because, your religion is as good as mine, your semantics is as good as mine. But if we actually look at what the algebra itself gives us, that's a good beginning. I mean, maybe later on you need to make further assumptions. That's always fine. But you want to see what it is that the algebraic system says. And here's where I'm going to end. I'm not going to spend too much time, but I want to show you where the fun begins. And this is where I actually hope that you do this. You should be doing this part, not me. But you're hiding there. So once you have a group like this, you can build a Hilbert space with it. And interesting things are going to happen in that space. In particular, you're going to find situations where you're going to have to, you can define an inner product. We're going to define the inner product in ways that are standard. And then we're going to see, all right, so under those conditions, what interesting things happen in that system. Now, that's going to go beyond the little phrases I've given you, because all I've given you are simple things like proud of John or Kill Bill and so on. But of course, look at what's coming out of my mouth and what you're processing. The intuition is that what we're doing here is, with those little components that are matrices that multiply and so on, you end up creating a vector space where more interesting combinations are possible, including things like the emperor of Rome was assassinated by Brutus, where you do a bunch of different things, okay? So the second half of that paper we left is showing you how, with this particular group that we explored, you can build a space where then, well, you end up producing, see, so far I've talked about this, kill Caesar, but we have to ask, well, so what happens when you add a subject to that, where kill Caesar now combines with a subject and you say Brutus killed Caesar? Or you can put a bunch of things in between. Brutus shall kill Caesar, and so on, right? You can get a lot of nuance there. So what happens then? Well, in our view, what happens is that whereas this first merge are matrix multiplications the way we've been seeing in the last half hour, these are actually tensor products. Now, of course, tensor products are fabulous beasts that, among other things, get you the dimensionality of what you combine shoots up, right? So the minute you go from, I don't know, you combine a 2 by 2 by a 2 by 2, you're going to get a 4 by 4. So very, very soon, you're going to have to start worrying about compressing that mess for familiar reasons for a crowd like this one. And that is music to our ears, because once you ask the conditions under which compression is possible, keeping the essence of the system, you end up finding. Do you remember, Roman, how many we had after you do the tensor product? So let's see. Let me do the computation with you mentally. We had 32 categories times 32, so that's 1,024 tensor product combinations, right? And then once you get that, which is another group, the paper shows it to you. Once you have that 1,024. If you actually look at sums of those matrices, you're now within a much larger space. You get 1 million plus. I forget how much, but it's 1,024 times 1,024. Some of which actually are equivalent, so it ends up being a fourth of that. But still, you're talking something like 250,000 possibilities. That's obviously extraordinarily too much. That's not what's going on. Now, once we apply the metric we show in the paper of compression under very strict conditions, we reduce it to 96 that satisfy certain strict symmetry conditions, out of which, again, only 32 end up reproducing the original system. This is where we get into these categories. I mean, so you end up going back to these categories. So it's kind of like an accordion. So first you get the tensor product, so the thing grows. But we have a condition that says if you're going to do that, you're going to have to immediately compress, but there's only a very few ways in which you can compress. So to just jump into what the paper will show you, once you see the ways in which you can compress, you end up, for example, predicting that only noun phrases displace. That if you were to do it with a verb phrase, you're going to get junk. You're going to get junk outside of the symmetry. So the system allows all these recursive combinations, and it is, we claim, it's a Hilbert space. But what ends up surviving under symmetry conditions is a minute proportion of the logical combinations. That's where the real fun is. Well, you can examine the paper. It would be very useful, actually, if you examine the paper in case we made a mistake and so on. We have it out there in, in cyberspace, but there's always, possibilities of making a mistake. Do you want to add anything to that?
No, not really. I'm just mentioning that this compression thing is a computational requirement, right? But we have to include it because otherwise, there is too much information, and at some point, the only combinations that are physically meaningful are the ones that can be compressed. Okay? Because otherwise, the amount of information will just explode. Right? So, and then actually after compression, it's something that will come back to it.
All right, so this is a very quick overview of the paper. Again, I feel, it's not a seminar, it's a class. But I don't know if this is enough for you to...
So how do you explain, for instance, that in English you say, shall I or I shall is not the same?
Yeah, very carefully. Let's see, we can use this. Not only is it not the same, but it involves what is called a transformation, which is what the paper is about. So let's start with the basic one. I shall, let's say, I shall eat beans. So the intuition is that this is going to project your verb phrase, and now we have a system to do that.
Tortilla de patata.
Tortilla, fine. So whatever, whatever you prefer. Actually, to be precise, because this is a beginning, for us, this is actually self-merge. So it's something like I eat beans, or I eat tortilla, which reduces to a phrase. Anyway, you start there. You're going to get... some question mark phrase, which if you look at our periodic table, it's going to be of this kind, what in the linguistic tradition is called inflectional phrase, because of that shall. And the shall itself, if you look at the... See, here, I don't think that in the paper we give you the justification for this. We have a monograph for that. If anybody's interested, this is where we argue this. But the word, the matrix that we use for what we call inflection is this one, okay? Which in our notation is minus IC2. Is one of the 32, okay? So linguists call this inflection, okay? But I want to emphasize that this is one of the 32, just as this is one of the 32, actually, okay? And same thing with this, but now, importantly, this, which itself is a noun phrase, I, the way this combines with this is different. This is now, so if this was matrix multiplication, this is a tensor product. So here you're going to get the projection that you get here, let me call it double question mark now, because we don't know yet what it is. It's going to be one of the things that Roman was talking about. If this was a 2x2 matrix and this was a 2x2 matrix because it's still part of the group, this is going to be a 4x4 matrix by the tensor product, right? So immediately by assumption, we're going to have to compress this, okay? Now, you wanted shall I eat beans, right? So this is going to have to be pronounced up here, right? So somehow this has to come further to this position. And incidentally, you did it with shall, but you could have done it with beans as well. You could have said, beans I shall eat, right? That's also a possibility, right? Or beans were eaten by me, or shall be eaten by me. All of those are possibilities. So our grammars have to allow for the possibility of taking a chunk like beans and combine it up here somewhere by way of another operation. Now, the operation we propose for those so-called chain formations is matrix sums. In other words, there's multiple steps you need to answer your question. First, you need to do a tensor product, which gets you to this higher dimension. Then that's going to get you a group of 1024 combinations, 4x4 matrices, and you're going to have to sum the ones that correspond to this particular operation. Once you do that, this is where we get into the compression process. The ones we claim that compress are only a very small part, that compress keeping the symmetries. Because it's not just compressing. Compressing isn't easy, but there are compressions that do not stay within the group, whereas there are compressions that do stay. So, long story short, after you're done with all these processes, you end up having an object that looks massively different from what you started with. And then you have to worry about its semantics. Why is it a question? Why is it a passive? Why is it a topic? And so on. That's what we talk about in the monograph in more detail. The difficulty we're finding is that linguists often don't think this way. And if you give them an answer like I'm suggesting to you, they lose the answer in 30 seconds into it, because the minute you say tensor product or compression, it's like, whoa, what is that? Well, you explain it and then say, oh, why do you need that? The reason we need that is we want to predict the possible combinations that exist, and we don't think that they are possible because they have a meaning or because they are popular or because they are statistically relevant, but rather because they fit an algebraic pattern. That's our bet. Okay, so that's...
The other guy in the photo. So this Chomsky, who is the other?
That guy?
Yeah.
Pauli, Wolfgang Pauli, who basically did what we're trying to do.
Oh, you are comparing the two sets.
Well, in part because it's his group, and of course you know that he was working with Heisenberg in the first use of matrices.
He was born in Vienna, right? Or there is a center, Pauli Center in Vienna.
I don't know where.
Heisenberg as well in Vienna. Pauli was Italian.
Pauli was Italian?
Okay, well,
No,
I don't know. Wolfgang Pauli, so I don't know. We can Google it.
He was born in Vienna, yeah.
Oh,
in 1900.
Yeah.
He passed away at the age of 58. So we have to rush.
Well, he got a Nobel Prize before dying, so I'm already not in that league, so.
Yeah, there is. I think it's much smaller. Yeah, but there is a Pauli Center. I can send you. Yeah, there is.
Anyway, any other? Let me ask you a question. I mean, is the gist of what we're trying to do? I mean, you're a mathematician crowd and so on. Is the gist of what we're trying to do even in the ballpark, or is this like la la land? You can be honest. I don't. Summertime.
This is a lot of la la land, but it makes fully sense, right? So. But on the other hand, I have a question more for these guys who are more from, say, informatics side and looking from computer science side, looking to text and patterns. So, because Word, I open my Mac, I write,
right,
and then Word says me immediately, well, this is wrong,
right?
Right. Maybe the shall is missing or the of is missing or
sure.
something is missing.
Sure. There's an algorithm that is telling you that.
So how do they do that? So
well, no. Of course, we know how they do that. The question, well, at least.
And is there any link between these two disciplines?
Absolutely, but of course, I'm preaching to the choir or the wrong choir. But here's the way I would pitch this. Suppose you wanna. Okay, let's just give a concrete example. Suppose I'm interested in Trump and walls. Okay. Because Trump builds walls, and that's wrong, okay? So suppose I'm interested in that. So what do? I go to Google and I say, okay, Trump wall, right? Something like that. I did it the other day. I mean, some of you can do it. You're going to get billions of hits because of that. So after the first page, who has the time to go beyond the first couple of pages? Which, of course, are organized according to some machine learning algorithm that tells you, well, those are the ones that get the most hits and so on. You're not going to get very useful information, among other things, because, this could be, yes, Trump building walls, Or even suppose you even make build, okay? Suppose you even introduce that. See, you're going to get all the possible combinations, including walls build Trump and a bunch of things that are not even in the same league, okay? Now, if what we are saying is correct, somebody should work with us or by themselves to begin to say, look, let's cut to the chase a little bit here. The relationship between the verb and the object, however it is you define that, we gave you a definition, but you don't even have to take our definition. Take your favorite. But the relationship between the verb and the object is way more important than anything else. You should, if you're interested in that, you should first of all search for, say, verb phrases. Now, granted, it's not easy to decide what a verb phrase is. It's easier in Spanish than in English because you can code, the agreement markers on the verb and so on. But those are details of execution. But suppose we have a way to find verb phrases. We should come up with an algorithm that starts by looking at verb phrases first and then worries about the subject, because that's going to give you a much more quality information than otherwise. And we have given you the math for this. Right? Because in one case, you're going to get a tensor product, the subject. In the other case, you're not. You're going to get a matrix multiplication. So is there a connection? You bet. If we could work on this for a summer, and we could come up with a prototype to show whether or not it's true what I just said. Is it the case that once we introduce the math I gave you, that when I go then look for Trump builds walls, that I don't get 1 billion hits, but I actually get, 100,000? And are they more meaningful? We can find out. That's the kind of project, that's why I wanted to work with you in things like this. Because we can find out. I don't know, maybe I'm wrong, maybe it's la la land, that's fine. Then we eliminate this particular way of doing things. But that's one very practical consequence of formalizing things this way or any other way. But this is a very particular way to do it based on standard grammatical patterns.
So you have some experience on text recognition, right?
Yeah, but we use machine learning is just statistical similarity. So you have a lot of examples.
Right.
You want to find the most similar ones, the closest ones.
And you give a metric of similarity and so on, which is not incompatible at all, right? Not incompatible. In essence, what... Is it said again?
Standard perspective. This is a
sure.
Hard work. You need a lot of data to process all this information, and this approximation is just more from theoretical parts, just to correct.
That's right. And to me, the most powerful next generation thing would be a combination of those, where we say, look, think of this as a prior to your statistical analysis in terms of machine learning. That's all. Now, again, please don't get me wrong. What you just heard here is a hypothesis. Right? We just gave you the paper. Let's see if it's right and so on. But I'm making two claims. One is this particular claim just to see if it works. But I'm making a larger plea, which is we should combine these things, whether it's this way or some other way, because right now we are not making use of natural language in a smart way. We're just starting, in essence, we're forgetting about 100,000 years of evolution of language, and we're saying, okay, let's start again. We have terrifically interesting algorithms, which they are. Who could deny that they're interesting? But we're starting with all the... You take my lexicon and combine it with all the possibilities and look at which ones are more similar because they appear more regularly. That's what we're doing. Again, it's fine, but we're saying, let's optimize that. Anyway, that's one way of looking at what we're doing.
And then there is, I think also there is a lot of subtlety on languages, right? And this is why, native people, it's not only how fluent you are on the way you speak, but how somehow how you are able to put so just I'm thinking in Basque, right? So for instance you say Gizon galanta. So galanta is actually coming from Latin, right? Galante.
Sure.
Galante.
Sure.
So galanta Gizon and Gizon galanta is not the same.
Of course.
But
of course.
I cannot explain how. But I feel the difference.
No. I can give you. I can explain. I'll explain it to you over lunch. But yes. But in all of those instances, though, the claim we're making is that there is a formal system that. In some instances as basic as this, because it doesn't get more basic than this. In some of those more nuanced position of adjectives, right, it is more lexical than syntactic, But regardless of what the explanation is in each instance, it is not like what you find in Basque. You go to Spanish and you don't find distinguished.
Right.
No,
I couldn't find this example in Spanish.
no, you can. You can. Oh, yes. If you say nuevo hombre and hombre nuevo, or if you saw, right, and they're going to have differences in meaning, and not only in Spanish. You get something like that. See, there are languages that don't allow both. But if a languages allow both positions, yes, then there are universals of meaning that get restricted depending on the position. Anyhow, point in all of this is that, of course, it's a tedious long-term task to figure out what the algebras are, but it would be useful to begin to make progress in that direction, because then we can program things, we can test things. I mean, the good things of what we're giving you is that if there is a mistake, you're going to find it, because the math is there. It's not hiding anything from you, right? I think that's useful, personally.
So here we have a collection of languages like Macedonian, Italian, Indian, Korean, Japanese, French, Arabic, but other than, of course, Catalan, Spanish, and the most, close.
Is there any language, is there anyone here who speaks a language that doesn't have verbs, nouns, adjectives, and pre or post position? By pre or post, I mean both, right? I mean, Guernica ko, de Guernica, but those are the same elements. Is there anybody here who speaks a language that does not have one of those four categories? I'd be very interested. Obviously, it's always important to find counterexamples.
Well, we usually classify another way, not both and objectives, but in other sentences. So I don't know if it's with MP, V, A.
What language are we talking about?
Korean.
In Korean?
Japanese is similar.
And what is it that you do not have?
We think verbs and adjectives are similar. So
Verbs and
we
adjectives.
just give them to one word. And yeah, so we basically divide by noun and verbs and other positions.
Yeah, sure. At positions I know that you have, but you're saying that the verbs and adjectives are not distinguished in Korean?
It distinguishes, but it's really similar because we just use noun and position, then it became verb or adverb.
Oh, I see. So you can derive the verb. Yes. Yes, that does happen in some languages where you get a combination and you get a new category by morphological combination. So in English, for instance, you have things like look up, and it's basically a verb and a particle. Yes, but it would be interesting to find a language that doesn't have adjectives or doesn't have pre or post positions. For example, I mean, so what we're trying to see is to what extent there are universals and to what extent they are robust. Or yeah, go ahead.
Can there be actually a language without nouns or verbs? I think that those two are kind of the nuclear.
Yeah, sure. Those are the central part. I mean, can there be? I mean, logically.
Nouns, I mean, perhaps you could live without a verb, but nouns at least.
Well, but if what you're asking me is could there be? Sure. I mean, I think logically speaking, there are many species that we're studying, vervet monkeys take, or there are a number of species that use something that they have a bark for a particular event. They don't have a lot, but they have what they have. So could there be? Sure. They're not human. Now, if you're asking me, could there be a human language that has, well, if what we're saying is correct, no. The answer is you have to have that. Again, that's a claim, so if it's wrong, you find a counterexample.
But it looks like there are several hierarchies of
Yes.
importance here.
Yes.
Verb.
Sure. So substantively, in the algebraic system, verb and noun are absolutely central. That's what this system is suggesting is the case. That's part of why we're proposing it that way. But you can also get into more subtle questions. Can you find a language where what displaces, like in a passive, is not a noun phrase? I mean, so we know you can say the empire was won or something. Can you do that with a passive, but with something else? I mean, that's not illogical.
So what do you mean
Sure. So for example, imagine so if I give you something like it was believed that Chomsky is smart. Okay? Now, you can do that, but you can also say Chomsky was believed to be smart. Yes?
That's true.
So what we have done here is we have long distance. Incidentally, long distance, because you can say Chomsky seems to have been believed to be smart, or Chomsky was seen to appear to... So you can do it recursively, okay? Now, here I am moving a noun phrase, Chomsky. Now imagine moving a verb phrase. The result is going to be garbage, but I'm going to write it there in green. Should have written it in red. So something like is smart was believed Chomsky to be. If that were grammatical, which is crashingly ungrammatical in English, right? Impossible. If it were grammatical, I would have passivized it's smart.
Okay, I see what you mean.
Now, we have to explain both what exists and what doesn't exist. Why the hell doesn't this exist? Right? Now, in the monograph we show, in our particular system, if you do this, you can compress. That's the answer we give. Right or wrong, that's our answer. And I'm kind of proud of that answer.
It's kind of a consequence in our case.
Yes.
Because compression was a computational requirement.
Yes.
We have to compress the thing, otherwise the thing blows up.
That's right.
And then you introduce compression and...
Yeah. So for us it's a theorem that only these guys move. Well, and it's interestingly enough, you don't find them. And by the way, if you try to move any other chunk, you're going to get garbage. For us it's a theorem. Anyway, this is where we are. I appreciate your patience. Oh yes, please.
So you introduced mathematical structure, algebra. So and then you talk about transformation operator. Do you have any idea what the eigenvalue, eigenvector was?
Well, we're
It's
looking.
very important in mathematics.
I agree. I completely agree. The short answer is I can give you the eigenvalue and the eigenvector, but I don't know its significance yet. That I don't know. I think that's... Okay, so our project is to first get this paper published, get the monograph published, and if we get a group to study this, those are exactly the right questions. I mean, again, it's easy to give you a number, but why is it? So far, I have only shown you the determinants, and the determinants have a meaning. The label of the category is the determinant. The traces also have a meaning because the inner product, the scalar product, is going to be the trace. But you're asking the next questions. Once you start looking at the corresponding characteristic polynomial, what is the root of that polynomial, and does it make a difference? In the monograph, we talk a little bit about that. So, in particular, in the monograph, we say the following, and this is more la-la land. We say the following: those matrices that are Hermitian, which I guess would be a real root, right, eigenvalue, those correspond to stable semantic observables. This is actually important for us. Now, if this was La La Land, imagine that, right? In other words, that's a very big claim that we're making. Probably not any bigger than the claims they make in physics when they tell you the Hermitian operators are important, not bigger than that, but still pretty big because it's equally puzzling. If it is puzzling in physics, why things happen to be that way, imagine in our case where we're still taking baby steps. But so the short answer to your question is yes, it's very important to us. Yes, it allows us to organize the categories, particularly in terms of the ones that are Hermitian, but we're still trying to see whether or not this is still la-la land or goes to some, more tangible places. Yeah. Yeah, but we can ask the question, and we can provide an answer, and at least you can evaluate it. Whereas if we didn't have a formal system...
So how do you explain then the evolution of languages in this algebraic context?
They don't. They don't evolve. They are. In other words, once you hit a mental capacity... Actually, let me take a step back. Does my dog have a vector space analyzing the world? Because one thing is to be able to conceptualize, another thing is to be able to communicate it. Of course, I have no idea whether my dog has it, but it's not a meaningless question, right? Certainly in the visual system, it's almost certain that they do. The question is, do they have a conceptual system anywhere like this? Does my dog have a verb? Does my dog have a notion noun?
But you say that, languages are not evolving, or you claim that they are not evolving according to your model, because your model is somehow taking a given, say, a space-time or time-location?
I'm saying two things, and I think I can blame Chomsky for this one. I don't claim that Chomsky would take this math seriously, although we think it is what he meant. But don't blame Chomsky for the math. But he has argued, I think convincingly, that the language faculty for humans evolved somewhere in the last couple of 100,000 years, not more. It's very recent. And once it evolved, it evolved. In other words, your mental representation of Basque and Spanish and English and so on is not very different from the mental representation of people that lived here 50,000 years ago. If we were to find how your brain works and we found those brains, they would be identical with regards to this.
The Spanish of El Quijote is not the same, the one we today.
Absolutely, but you didn't say it's not the same, which of course is true. You said it evolved. That's what I'm objecting. I don't think it evolved. I think it changed. It's a dynamical system. It actually is interesting how little they change. Because if you go back to El Quijote, you still find verbs, adjectives, prepositions, and what did I miss? Nouns, right? What happens? Yes, certain words are different. Yes. Okay, so that's interesting how the words change. So this is why I think machine learning.
Of some words.
Sure. But this is why I think machine learning has to, we have to both dance this tango together, right? Because all of that would be saying, yeah, sure, this is the dynamic. It's open. I'm just giving you the basic algebra. Now, how that algebra materializes, that changes massively. The phonology, we used to say farina, now we say harina. Sure, all of that changed, for sure. But I would object to it being an evolution. I don't think it's an evolution, it's a change. Any more than the weather, when it changes, does it evolve? Well, it changes, right? There was a storm 2 weeks ago, and now there isn't one. Hasn't really evolved not in the Darwinian sense, right? Now, language did evolve, and it stayed language. For how long? Who knows? Because we haven't yet understood how it evolved.
Some people say that this was a discontinuity, in evolution, that at some point,
yeah.
There was capacity mathematics,
yeah.
music, and all these things came together, and it looks like there was...
Yeah, there seems to be a phase transition of some sort that gave us that. Yeah, that Berwick and Chomsky would take that view. Yeah.
So I was wondering, so there are some monkeys or chimps or gorillas that you can teach them human language, sign language.
Excellent.
Do you use this also all this structure, or do you take
yeah.
it as a...
Okay, so let's backtrack here. There are a few instances of trained bonobos, orangutans, chimpanzees, who have acquired a vocabulary of signs. Last time I checked, it was around 500, which is not trivial, okay? In fact, even dogs. I've seen of one dog that was able to get around 900 or so correlations between certain, in the case of dogs, it wasn't a sign, but it was some visual image or some correlation. So yes, that is possible in several mammals, not as successfully, but also quite successfully in some avian models of the parrot sort. There are parrots that could get you, I don't know, a couple of dozen or more symbols. Now, So that's very good news and very interesting, right? Because you have another model that is capable of doing something similar. Once you look at the combinations, though, they're pretty haphazard. So far, I haven't seen yet any systematic combination that retains the algebra we're talking about. That doesn't mean it's not there. Maybe we haven't found it yet.
I mean, I found, because I saw a video of a gorilla called Coco that was...
Coco, yes.
Was speaking, actually, but her grammar was a bit poor, though
yeah.
she was producing her own...
Right, right. Oh, yes, yes. And so your question is absolutely apropos, and we haven't done it yet, or we haven't done it, because I don't know that people working with Coco would follow or be interested in what we're doing. But your question is totally appropriate. Does what we know about Coco correspond to some of the combinations? If I had to bet, I would bet that it's all at the matrix multiplication and not at the tensor product. But I don't know. This is even wilder than anything I have said before. It's a good question, and I think it is very well worth asking. Because part of what Roman is saying about the discontinuity is that obviously this didn't happen miraculously, right? I mean, what we're using is a combination of vocal learning, visual gazing and pointing for reference, theory of mind, a variety of elements that you can find separately in other animals. So what is it that in this particular species in the last couple of 100,000 years, how did it crystallize into what we're using? That's the big question we all have. I think we're making slow progress, and cases like what you're talking about are totally relevant. Yeah.
Comparing them with the lower grammar complexity of Coco and our grammar complexity, do you expect that there might be some other, let's say, category or combination missing that could enlarge our expression?
Oh yeah. I mean, if what we're saying is right, look at what Roman was saying. The reason we compress, the reason we get what we get is because we need to compress back. Now, imagine for a moment a superstructure that didn't have the memory limitations we have, where you could handle n by n matrices. If we're right, you can only handle 2 by 2, 4 by 4, and you start already getting shaky. But imagine an intelligence that can do 10 by 10, any combination. Sure, we would expect, I would expect that things like this would be possible. And I would even say something wilder than this. I actually suspect that geniuses like Chomsky and Mozart and so on, that perhaps part of what is happening internal to their head is that they have the ability to put together larger combinations than most of someone like me has. They may not have an easy time expressing it because the particular language faculty we use has these limitations that we're talking about. But is it possible in principle? For sure. Once you have an algebraic system, it allows you to get into larger combinations. I can see why not. Now, of course, because the argument that Roman was putting forth is combinatorial, right? It's computational. It's telling you, look, if you get more and more tensor products, this thing is going to explode in complexity. Well, but that's depending on your algorithm, right? If your algorithm has unlimited memory capacity, why not? Yeah. I don't know if you want to add anything to that or you
Yeah, I mean, I don't see why not. It shouldn't be possible to extend these to
right.
some more complications. Or perhaps to consider subsets of this structure for more like what we were saying about Coco.
Exactly. The Coco situation would be sort of the opposite, right? I mean, if perhaps Coco is just using the matrix multiplication part, not the larger ones that we use, but what you're asking is, could you use more? Sure.
Yeah, but for example, Coco was not producing future or past.
Right. That's correct. So I think, again, remember Enrique's point about half an hour ago? Coco would be at the level of having which guys? I mean, I guess something like this. The commutative one, something like this, something like that, and something like that, period. That's the hypothesis. I obviously have no idea. I do know that he couldn't produce future and past. Future and past would be on the non-commutative part, right? So that's an interesting hypothesis you're putting forth there. It's totally consistent with everything we're saying. Now, is it true? We would have to do the research and find out. But yeah, that's the spirit of the program. Guys, I think I've exhausted you. Thank you. Thank you.